Alright guys, so in this lecture we are going to be looking at organic spectroscopy. Now, our interest will be on NMRO spectroscopy and then the IRO spectroscopy. In our previous semester, we've actually looked at the UV spectroscopy, where we talked about the Woodward-Fisher rule and some other things, where we said that the UV spectroscopy is a spectroscopic technique that is used to assess the extent of conjugation in an organic compound or in an organic molecule. So in this lecture, we are going to be looking at the NMRO spectroscopy. But before then, let us do a quick recap of what we learned in our previous level. Now, we said that spectroscopy deals with the interaction of electromagnetic radiation with a material. The interaction between an electromagnetic radiation with a material is what is called what? Spectroscopy. Now, most times, we define spectroscopy as the interaction of a material with light. When we talk about the electromagnetic radiation, most times we are usually talking about the light. Now, of utmost importance, like I told you, the ones we are going to study in are the NMRO spectroscopy and then the infrared spectroscopy and then the ultraviolet spectroscopy. Now, there's what is called the electromagnetic spectrum, which of course at this level we should know what the electromagnetic spectrum is. Now, we said the electromagnetic spectrum consists of different regions that corresponds to different frequency and different wavelength. Is that okay? The electromagnetic spectrum consists of different wavelengths, different regions that correspond to different frequency, which is this, and different wavelengths in a particular order. Now, each of these spectroscopic techniques use electromagnetic radiation from these various regions in the electromagnetic spectrum. For instance, if you look at NMRO spectroscopy uses radio frequency. This is NMRO. Sorry, this is supposed to be radio frequency. All right. So the electromagnetic radiation used by NMRO is the radio frequency, and it has a wavelength of around 10 meters and a frequency of around 10 raised to the power of 7 hertz, which is equivalent to 100 megahertz. Now, the infrared region is the region that actually gives the electromagnetic radiation that is used in infrared spectroscopy, which is IRO spectroscopy, and it corresponds to the frequency of 10 raised to the power of 10 raised to the power of 13 meter, 13 hertz, and the wavelength of 10 raised to the power of -5 meter. And then the ultraviolet is for UV visible. You can see it ultraviolet / visible. That one is a spectroscopic technique that uses electromagnetic radiation from the ultraviolet or the visible region of the electromagnetic spectrum, which corresponds to a frequency of 10 raised to the power of 15 and a wavelength of 10 raised to the power of -7. Now, the most important thing we need to know is spectroscopy deals with the interaction of electromagnetic radiation with material. Now, if the electromagnetic radiation is that from radio frequency region in the electromagnetic spectrum, we say that kind of spectroscopy, you call it the word NMRO spectroscopy. However, if the electromagnetic radiation that interacted with the matter or the material is in the infrared region of the electromagnetic spectrum, then we say that spectroscopy corresponds to what? The IRO spectroscopy. And then, of course, if the electromagnetic spectrum, the electromagnetic radiation that is actually interacting with the material is from the UV visible, UVVs, you call that UV visible spectroscopy. And each of these three regions have the instrumentation for the NMRO, for the IRO, for the UV spectroscopy have different property they wish to actually unveil in a molecule. For instance, the NMRO they actually deals with the nature of protons and the chemical environment of those protons, while the IRO deals with the functional group. What functional group do we have in a molecule? For instance, is it an alcohol functional group? Is it a carboxylic acid functional group? Is it an amine functional group? IRO spectroscopy will give you that information. Then UVV spectroscopy will tell you the extent of conjugation of that molecule. How many conjugated double bonds do you have? Are you getting it now? So that is that for the electromagnetic radiation and the electromagnetic spectroscopy generally. So we are going to be dealing with these three in this session, which is this semester we are currently. All right. So what are the application of organic spectroscopy? The application of organic spectroscopy are: 1. Structural determination. Spectroscopy actually helps us to determine the various structure of an organic compound by applying knowledge from the three different spectroscopic techniques that I've listed earlier, like NMRO, IRO, UVV, will actually tell you the structure of the compound. That is structural elucidation. You did a practical experiment and then you got a product, but you don't know what is in that product. What do? Pass it through the NMRO, the IRO, UVVs, and also the mass spectroscopy, which is mass spec. Are you getting it? That will also give you information about the structure of an organic compound. Now, to characterize the material. When I talk about characterize the properties of those material, is that okay? It will help you to characterize the material, the properties of those material. Now, to enable the physical and chemical property related to the structure, and therefore safety, and then to monitor the progress of a reaction. These techniques NMRO is usually used. NMRO will help you to monitor the progress of a reaction. Like you actually carry out a particular reaction in kinetic studies. When it's actually talking about kinetic studies, you want to know the product that you've actually gotten. You can use NMRO techniques to check that out. And also the purity of materials can be checked, and then routine checking of structures. So these are the various applications of organic spectroscopy. Is that okay? Now, the next thing we need to know now is the general idea behind NMRO spectroscopy. All right? General idea behind NMRO spectroscopy. Now, what is NMRO? NMRO means NMRO means nuclear magnetic resonance. So what we are actually studying in NMRO is what? Nuclear magnetic resonance. Now, you should place emphasis on this word here, resonance, because we are going to talk about it in detail later. Now, my dear students, what do you understand by nuclear magnetic resonance, and what is the principle behind the NMRO spectroscopy? Now, you've actually learned before now that NMRO spectroscopy is used to characterize an organic compound, to know the different kinds of proton. In that case, you call it the proton NMRO, or you can call it HNMRO. Or to know the nature of the carbon in a molecule. In that case, you call it what? The carbon NMRO. Is that okay? But the carbon is not just ordinary carbon, but is an isotope of the carbon. So you call it the carbon-13 NMRO. We are going to know why they use carbon-13 and not carbon-12 as the lecture progresses. Now, we said NMRO means what? Nuclear magnetic resonance. Is that okay? Basically, the two types of NMRO we are going to treat are proton NMRO, which gives us information about the different chemical environments of each proton in an organic compound, and then the carbon NMRO, which gives us information as to the nature of what? Carbon. Now, let us take proton NMRO and let me use that to explain. Now, for instance, proton is H plus, and it is what? Positively charged, right? So it's actually a charge. Proton is H plus and it is positively charged, so it is a charge. Now, Benjamin Franklin classified charges into two. We have the positive charge, which we can indicate with positive, and then we have the negative charge. Is that okay? We have the positive charge and then we have the negative charge. These two, we call them electric charges. And of course, you know the relationship between these charges, the positive and the negative. What will happen to them? They will what? Attract. True or false? Exactly. Now, a charge, especially that of the proton, you can see here, have what we call a spin. The spin, the nuclear spin. So you call it H positive. It has what we call what? A spin. Is that okay? So this charge you see here does not just stay where it is, but rather it has a spin. So if you have, let's say, so many proton here, right? Let's say this is a proton. One may spin in this direction. Are you getting it? Then this is another proton. Another one may spin in this direction. Another one may spin in this direction. Different direction. All right? They may spin in various directions. Now, because they are spinning, what do you think will happen? There is a magnetic field around them. We define magnetism as what? What did we define magnetism as? We define magnetism, we say a magnet is formed by the what? By the movement of electric charges. Right? We define a magnet as the movement of what? Electric charges. So, as these protons are spinning, cause there are electric charges, so a magnetic field will be what? Will be developed around them. So it means that this proton that is spinning, it has a magnetic field around it. This one that is spinning also has a magnetic field around it. This one that is spinning also has what? A magnetic field around it. Is that okay? So that is the general idea on spinning. All right, let me try to explain something. Like we said, that anything that is spinning has a magnetic field around it. So you agree with me that all these we noted earlier, they have a magnetic field around them. Can be in this direction, can be in this direction, can be in this direction. Now, each of these ones you see here, they are positive charge. Now we say they have a magnetic field around them. Why? Because they are spinning, right? They are spinning, so they have a magnetic field. Because say magnetism is the what? The movement of charges. If something is having a spin, it means it's actually moving, right? Now, listen. Now, in a situation where there is an external magnetic field, let's say you apply an external magnetic field. Let me draw a diagram to illustrate this. So let's say you have something like this. One is going up, the other one is coming here, right? And let's say you have two things that are this whole thing here that are spinning, right? Now, let's say you now apply an external magnetic field, says something like this. Let me use this one. This is an external magnetic field, and this is the direction of the external magnetic field, right? The external magnetic field is in this direction. You can see it. Now, two things can either happen here to this molecule. Let's say there are four molecules here. Let me just use this illustration. Let's say there are four molecules here. Now, two things can either happen. Now, some of the molecule may spin in the same direction with this stuff here, while some will spin in the opposite direction with this stuff here. So some of them will be spinning in the same direction. So this one that you see them, they are in different directions. They can only have two spins. Now, when does this happen? When an external magnetic field is what? Applied. So that will only happen when an external magnetic field is applied. Note that something has its own spin around it, but whenever an external magnetic field is attached to it, it can have two directions of spin. It can either spin upward or spin downward. Now, in the same direction. So if it's spin parallel to it, you have something like this. You'll be having something like this. Be having something like this. All right, which is positive charge, positive charge, positive charge. Then it can also be in the opposite direction. You see these ones, I'm just using this. Okay, let me use 2 since we have 4 there. So some can spin in the same direction as the magnetic field. Recall that this is a magnetic field, or let's say external magnet, right? This one can spin in this direction, opposite in the direction with the magnetic field, and then this other one will spin in the opposite direction as the magnetic field. Now, the ones that spin in the same direction as the magnetic field, we call them the low energy. So this one here, low energy spin. Let me use low energy spin. Why this one? They are the high energy spin. So it means these protons here are higher in energy as compared to these ones here that are lower in energy. Now, my dear students, listen. This spinning we are talking about don't just occur like you see the direction. It occurs like a spinning top. How many of you have seen that this thing we used to do when we were young, where we take battery cover, the battery cover for all those big batteries we put in our torch, those old age, right? And then we now put big biro in the middle. The big biro cover in the middle, we break it and put the cover in the middle. The middle of that this thing usually have a hole in the middle. So we put the big cover in the middle, and then we start spinning it. Now, when we spin this thing, you see that this thing will be rotating very fast. Why the big this thing will be the what? The under. Are you getting it? Will be the what is holding it on the floor. Why the top will be rotating. That is how these protons are when an external magnetic field is attached or is actually exerted on it. Is that okay? It looks like something like this. So when the external magnetic field is exerted, it looks like what? A spinning top. Now, in a situation where the spinning it's still the same thing with what we've actually described. In a situation where the spinning is in the same direction as the magnetic field, you call it a low energy spin, right? What we are saying is something like this. Let's say something like this. It's actually spinning, right? Now, this is the Earth's magnetic field. The Earth magnetic field is actually in this direction. You can see it. So you see that something is spinning in around the Earth's magnetic field. You can see this one here. What I mean is that this thing they turn. Are you getting it now? And it's spinning in this direction. Now, how do you know the direction of spin? It's very easy. You can actually see it from here. Let me draw an arrow. You can see an arrow. This one is telling you the direction of the spin. You know when something is spinning, you can actually see the direction here. It means it's spinning this way like this. Are you getting it? Spinning in this direction. It's continuously turning. So in this case, you also call it the what? The low energy spin. So this one is lower in energy than the high energy spin. Okay, let me draw and designate that for the high energy spin. The high energy spin is the one that is opposite the low energy spin. So when that one is spinning that way, this other one here is spinning this way. Let's just say something like this. Of course, you know the Earth magnetic field somewhere around here is at the center. It's acting downward, perpendicular to this thing. while the proton spins in the direction of the Earth magnetic field. So you have this, it's also spinning in this way. So you actually see this thing. So as it's spinning like this, you can actually see that it's spinning in opposite direction. Why this one is spinning in this way? You can see it's spinning in the direction of the what? The external magnetic field. What are all these? These are protons. Is that okay? What are all these? These are what? They are protons that we are actually looking at. This is a proton. This is also a proton. These are two protons. Are you getting it now? Now listen. Something in the low energy spin and the high energy spin. Now the energy difference between the two energy states is called the change in E, change in energy. Are you getting it now? The energy difference between the high energy state and the low energy state is called the word change in energy, which is designated by what? Change in E. Now, from what you learned in chemistry, we are told that change in E, right, is equals to what? H times frequency, right? H times what? Frequency. That is the change in energy. Now, I just don't want to know what this frequency is. This frequency, which you see here, is called the precessional frequency or precessional frequency. This is called the precessional, something like the frequency. Are you getting it now? This is called the what? The precessional frequency of this whole thing you see here. Now, if you can see this very well, this one here, like we said, this one here align with the magnetic field. Is that okay? This one here align with the magnetic field. So this nucleus here align, this proton nucleus here align with the magnetic field. Are you getting it? The one that align, we say their energy is small. Why this one is opposed to the magnetic field. So this one is opposed to the magnetic field, is opposite the magnetic field. Now, my dear students, at this point in time, what do you now need to do? We say change in E is equal to what? HV, which we said this thing here is not V, it's called frequencies. The Planck's constant times the frequency. The frequency is called the precessional frequency. As this thing is moving around here, it is actually precessing. That's spinning around the axis, the Earth's electromagnetic, the Earth magnetic moment. This one is actually spinning around it, like when something is turning. You know, although a stripper in the club, you know that pole they used to put in the middle, then the stripper is turning around it. That is how this electron, this proton is actually spinning. Now, the frequency with which this stuff is spinning is what we call the what? The precessional frequency. Is that okay? So that is what we call the precessional frequency. This one also have its own precessional frequency. Now, one thing you should know is that the precessional frequency does not change, but rather the speed changes. The precessional frequency does not change, but rather the speed does what? The speed changes. Now, the precessional frequency also, my dear student, is directly proportional to the magnetic field that is irradiated with it. Is directly proportional to the what? The magnetic field of the magnet irradiated with it. So the higher the magnetic field, the higher the precessional frequency. Is that okay? Precessional, like I told you, precessional frequency does not change, but the velocity of the precessional frequency actually does what? It changes. So let's understand what we are saying here. We say a proton can have a spin because that proton is a charge, and the movement of charges is what we call what? Is what gives rise to magnetic field. So that proton can have its own magnetic field. However, if an external magnetic field is placed in that proton that has its own small magnetic field, you know, of course, the external magnetic field will be higher than the magnetic field of the proton itself. Is that okay? Let's say you have this as a proton spinning in this direction, or let's say this is another proton spinning in this direction. Then you put a magnet of higher magnetic field. What will happen? It will actually align this proton with itself or against itself. So in a situation where the proton is aligned against, you call it opposed. and that is the high energy. Then when the proton is in the line with the external magnetic field, you call it what? You call it low energy. Is that okay? So that is that. Now we have learned about the change in energy. The change in energy is the difference in energy between the high energy spin and the low energy spin. Now this change is very, very small. Is that okay? This change in energy is very, very small. I would say that the precessional frequency that is proportional to the what? To the magnetic field what actually irradiated, or the magnetic field that is exerted on the precessed, or the magnetic field that is exerted on the proton itself, or on the charged body. Let's not use a proton, let's use a charged body, on the charged body. Now, what is the essence of NMRO spectroscopy? Now, in NMRO spectroscopy, what they do is they know that, okay, we have a sample. That sample contains proton. Let's put a magnetic field there. So they put an external magnetic field, and then the sample begins, the protons in the sample, or the charges in the sample begins to what? To precess. Right? Now, when it precess, they will now add what is called electromagnetic radiation. Like we said, electromagnetic radiation is the what? Interaction of electromagnetic wave with matter. So this is the matter now. In the matter, you actually add the magnetic field first. Then you now add radio frequency radiation. That means frequency corresponding to the radio wave in the electromagnetic spectrum. Now, when you now add this radio frequency radiation, what will happen is this something that was precessing, it has its own frequency. The frequency of precession must be the same with the frequency of the must be the same with the frequency of the radio wave that you actually what exert. That is, this precessional frequency must be equivalent to this frequency that you are actually what exerting. Is that okay? This radio frequency must be equivalent to the frequency you're exerting to this something. You know, this thing is actually precessing. As it's turning around with a particular frequency. That is called the precessional frequency. Right? I've explained that the frequency with which this thing is actually turning around the Earth magnetic field is called the what? The precessional frequency. What I'm not saying is that you cannot add an external radiation corresponding to the frequency that was precessing before, the precessional frequency. Is that okay? Now, when something absorbs energy, what will happen? It will actually be exerted to a high energy state. So this low energy spin will be excited to a high energy spin. So what will happen? There will be what? The magnetic field will be what? It was spinning in this direction. Once you add the radio frequency, it will now spin in the opposite direction. So it has been promoted from a lower energy to a higher energy. Why? Because you added what? Radio frequency. Is that okay? Now, at this point in time, after some time, what will happen? When something gains energy, after some time, it falls back to a lower energy. This one will now fall back to a lower energy. That radiation that is given off is what is measured in the what? In the detector of the NMRO spectrum to tell you the different structure. Is that okay? That is what is measured in the detector of the different NMRO. Now, let me tell you, every proton has a precessional frequency that is peculiar to it. And there are several factors that actually affect this precessional frequency. Is that okay? Every proton you see have a precessional frequency that is peculiar to it. So, by the time that this thing comes out, and then let's say this thing you got in your detector, the frequency you got in your detector correspond to CH2. You know that, okay, now CH2 now that place of the molecule. Then it correspond to, let's say, CH3. You know that, okay, it's CH3 that is at that place in the what? In the molecule. Is that okay? So that's the general idea in NMRO spectroscopy. Now, because the precessional frequency must be equal to the radio frequency that is exerted, you say that they are in what? In resonance. That is where the word resonance came from. You say they are in what? In resonance. Why? because the precessional frequency is equal to the radio frequency that is exerted for the something to be excited from this small or low energy state to a high energy state. Is that okay? So that is the general idea. So the general idea in spectroscopy, NMRO spectroscopy, is that, let me explain. The general idea is that you have a molecule, right? This positive charge spinning in different direction by virtue of their charges. Now, at the end of the day, what do? You put an external magnet. So external magnet comes in, and then they can either spin in the direction. Let's say the external magnet is spinning in this direction. They can either spin in the direction of the external magnet or spin in the opposite direction, right? Now, at the end of the day, if you now exert a radio frequency to it that correspond to the precession of this molecule, the one that are in the lower energy spin will go to what? High energy spin. And then after some time they will emit that radiation, which is now actually what they detect in the what? In the detector. Now, because the radio frequency you exert must be equal to the precessional frequency for these things to what? Be promoted, you say that the radio frequency and the precessional frequency are in resonance. That is where the word nuclear magnetic resonance came from. Is that okay? So that is that. Now, like we earlier said, that our V is, which is the frequency, is direct proportional to the what? The magnetic field. Is that okay? It's direct proportional to the magnetic field. And V, if you remove the proportionality constant, this is direct proportional. If you remove the proportionality constant, you are going to have this frequency is equal to a ratio called the gyromagnetic ratio. Then BO divided by 2 pi. This is the frequency now. So the frequency, precessional frequency rather, has this formula. This is the formula for precessional frequency. Alright? Like I told you, the precessional frequency is equal to this gamma sign. The gamma sign means gyromagnetic ratio. And we are going to explain what the gyromagnetic ratio is later. And then BO is the strength of the magnetic field. Now, at this point in time, if we substitute all this into this equation, the equation you had was what? E is equal to what? H times frequency, right? Now, we already said that our frequency is what? Gyromagnetic ratio, BO, all over 2 pi. So, at this point in time, what do? We put this all into the equation, and then our E is equals to H. Wherever we see this, we put in this entire thing here. Alright? So this will give us HBO all over 2 pi. So this is the formula for calculating the what? The change in energy that is associated with promoting a proton from the low energy state to what? The high energy state. Are you getting it now? So that is that. Thank you very much for your time. We'll see you in the next lecture.